Thank you for the kind introduction. Can we get the slides, maybe? Oh, wonderful. So thank you, everyone, for coming so early in the morning. I'll be talking about Ouroboros and Ouroboros Praos, which are two provably secure protocols, proof-of-stake protocols, that are designed to achieve consensus in Cardano. So, and I'm a research fellow employed by IOHK. So I come from academia. My background is in cryptography. So before I get into Ouroboros, let's discuss the relationship between Ouroboros and Cardano. So maybe in the proud tradition of Michael's talk yesterday, let me ask you, who of you has heard of Cardano? Okay, so quite a few people. And who of you has heard of Ouroboros in this context? Okay, significantly less people, which is to be expected, which is good, because then you will learn something from this presentation. So let me clear out the relationship between Ouroboros and Cardano. So Cardano is a decentralized public blockchain, an existing one, which currently supports a cryptocurrency that is, I believe, like 7th largest by market cap or something like that. Changes every day. And the goal of this project is to build a better decentralized public blockchain with scalability, interoperability, on-chain governance, and much more. But most importantly, to make all the design decisions in this project based on rigorous theoretical understanding, so coming from science. So I'm coming from academia, and also the whole research department in IOHK are people that are currently or in the past affiliated with academia, and the goal is to base our design decisions on peer-reviewed research papers that were published on international conferences that focus on the subjects that are relevant to the question of cryptocurrencies and blockchains, which is a very interdisciplinary field. So this covers cryptography, of course. I would say, I would like to say in the first place, because I'm a cryptographer, but of course it also covers distributed systems, cloud computing, programming language theory, eventually, of course, also law, economics, and so on. So this is Cardano. It's a huge project, and Ouroboros is just a part of it, but it's a part I've been working on together with my colleagues. And what it is, it's a proof-of-stake protocol. So it's a protocol aiming for achieving consensus on the Cardano blockchain, following the proof-of-stake paradigm. Don't worry if you don't know by now what this is. This is something I will discuss. And it's provably secure. It has been published in a cryptology conference, and it is used as a mechanism in Cardano. And since this is the area I have been working on, this will be the only part I will be discussing today. So Cardano is much more than Ouroboros, but today I will try to give you an intuition of how Ouroboros works. And Ouroboros is like the foundational layer of Cardano. First, let me mention that Ouroboros these protocols are joint work with Aggelos Kiayas, Alex Russell, Bernardo David, and Romano Olejniko, which, as you can see, are affiliated with either IOHK or a renowned research university, or both. And these gentlemen actually came up with the first version of Ouroboros, and I joined the team when we improved it to a new version, Ouroboros Praos, that I will be talking about later. So the roadmap for today, at least for this talk, is as follows. So first I will briefly tell you something about Bitcoin and proof of work. I'm sure you know how Bitcoin works, but we will try to summarize it from a very high level, and also to be able to draw some parallels to later be able to talk about proof of stake, which is the concept that Ouroboros is trying to achieve and is achieving. We will try to motivate why Bitcoin is probably not the final answer to the question of how to design cryptocurrencies and blockchains, and that's why proof of stake might be the way to go. But it turns out that designing a proof of stake is no easy feat, and I will discuss typical problems that one can run in when trying to design it, and then I will give you a high-level overview of the actual Ouroboros protocol and also of the improvements that were put in place when we moved from Ouroboros to Praos. Okay, so let's start with Bitcoin as a warm-up. So we all know what Bitcoin is. It was proposed. We don't know by whom. At least I don't know. It's an electronic currency, and it has two novel. The novel contribution of Bitcoin is connecting a lot of dots that were present in the academic research before. But the main novelty is being able to maintain a decentralized ledger and this is possible if a particular novel security assumption is met. And this assumption, as you probably all know, is that the majority of computing power is in the hands of honest parties. This is a very nice picture from a recent paper, a survey paper by Narayanan and Clark in 2017. And it shows how Bitcoin, which is the line somewhere down here in 2008, how it connected a lot of research lines that were present in academic literature from the 1980s and were in a sequence they were developing until Satoshi Nakamoto, whoever that is, joined these dots and came up with this system, which is an ingenious proposal, of course. And it inspired a huge amount of follow-up work, and this work can be split into into several categories. So a lot of new currencies came up after Bitcoin. This is something you, of course, know. And some of them aim to give you a richer Turing-complete transactions. This would be the smart contracts. So Ethereum is a prime example of this. Some aim to give you better privacy, and some try to improve the consensus mechanism. Of course, Cardano tries to improve on all of these, but I will be talking about the different consensus mechanism. So let's discuss why we actually need a different consensus mechanism. So how does the one in Bitcoin work? So what Bitcoin provides you, the first question you should ask is, what is actually what Bitcoin provides you? What is it that the whole system gives you? And what it gives you is a way to maintain a distributed ledger by collection parties that are mutually distrustful, but they do want to agree on this ledger. And this ledger should have two properties that are formally defined in the literature, actually. Persistence, which means intuitively that once you put something into the ledger, it's there. So these transactions are immutable. And liveness, which means that if you want to put something into the ledger, it will get there eventually. So maybe you have to wait for some time, but the transactions have to get in at some point. Otherwise, it would be easy to construct the ledger. It would just do nothing. And this persistence and liveness has to be achieved in an environment where parties just come and go, and they don't need any certification or anything like that. And some parties might even try to disrupt the system, of course. We want to be able to act securely in an adversarial environment. And Bitcoin does this via the blockchain data structure, which looks as follows. You just have something that is called a genesis block. This is denoted by the star here. It's an agreed upon starting point. And from that on, we have blocks that each of them, except for transactions, contains also a hash of the previous block. But the problem comes when we want to decide how to extend such a blockchain. Because the parties have to agree on what will be the next block. And this is outside of what the theoretical computer scientists have been looking on before, or most of them at least, because majority of players, like saying, let's do what the majority votes for, this makes no sense anymore, because we have this setting, permissionless setting, where parties can come and go. And so there is something called a Sybil attack, which means that the adversary can just create a million new identities, and suddenly he can dominate the voting, and he is in control of the majority. So just counting votes is not a good idea. And how the Bitcoin deals with this is by combining two ideas. Proof of work, which means that every block needs to contain a proof of work. I'm sure you have seen how this works. Basically, each block has to contain a work nonce, that the party has to find, the miner has to find, so that the outcome has a sufficient number of zeros, which proves that the party has done a lot of work to find these nodes, because this can only be found by chance, basically. We don't know of a better way to find it. And an important ingredient is the longest chain rule. So if I'm a party participating in the protocol, if I see a lot of chains coming from the network, I simply take the longest one, or the one that contains the highest amount of work, and I consider this one the current state of the ledger, maybe with removing some final blocks at the end to achieve this persistence. So this is a Bitcoin solution, and how the protocol works, just to be able to compare it later, it's actually amazingly simple. You just, when you are participating in the protocol, you just collect all the transactions that you see on the network, and also all the blockchains that you see on the network. You adopt the longest blockchain that you have seen as your current state, and you try to mine a new block by doing this proof of work process. And if you succeed, you just broadcast it, and everyone adopts it as well if it's the longest chain. Very easy. The thing that Bitcoin achieves is called eventual consensus, which means, as I said, the deeper the transaction is buried in the blockchain, the more stable it can be considered. Because if we have an adversary that would try to create an alternative history and maybe do a double spending, so if there would be a transaction in one of the blue blocks after the split, and the adversary would try to create an alternative history, he would have to create a longer chain, right? Because all the parties adopt the longest chain. And to be able to do so and to outgrow the actual blue chain, he would have to have more computing power than the honest parties. This is at least on a very intuitive level what is the security argument for Bitcoin. So as long as the adversary has less computational power than the honest parties, this is very unlikely to happen. And so the deeper a block is, the more immutable it is. So this is what is eventual consensus. But you can also see this as an implicit randomized leader election process. So basically, all the parties that are participating in the protocol, they are just doing their computation. They are trying to solve the proof of work, and basically, you can see this as an election of a leader who will be able to create the next block. And your probability of becoming a leader is proportional to your hashing power. So you can see it as an election process that is based on your hashing power, as opposed to just one man, one vote approach, or one citizen, one vote. So what's good about Bitcoin is that it's remarkably simple, as I said, and it solves a problem we thought would be very difficult, thanks to this, or even impossible in some models, thanks to this new assumption of honest majority of computational power. And there is a lot of formal analysis into why Bitcoin works, but I will not go into that. But since I told you that I will try to convince you that this is not the final answer, one of the problems with Bitcoin is that it relies on this computational race. People are trying to invest as much in hashing power as they can. And this honest majority of computing power is critical for the security. And this implies that as Bitcoin grows, the amount of, as price of Bitcoin grows, the amount of rewards grows, and therefore it's also economically rational to invest more into mining. And so this doesn't scale very well. Already now, Bitcoin, these numbers are very, very rough, and I'm sure you've seen some of predictions of this type already, some of estimates of this category. So I'm not claiming these numbers are exact, because it's very difficult to estimate, but roughly they make sense that Bitcoin consumes energy on the order of gigawatts. People estimate vary between 0.5 gigawatt to 5 gigawatts. This is several blocks of a nuclear power plant, so that actually matters. Or it's 1 million US households, or a small country. And what is even more worrying, at least for me, is that, let's say in the last 6 months, these estimates have tripled. So it seems that as the system grows, the demands grow as well. And also, Also the security of Bitcoin, if you would ask how much would it cost you to do a double spending attack on Bitcoin, if you would assume a liquid market for hashing power, which of course is probably not true, but if you would be able to rent hashing power, then making a double spending attack would just cost you as much as the rewards for, let's say, 6 blocks in Bitcoin, right? So it's not proportional to the price of all the Bitcoins together. It's only proportional to the amount of rewards in a particular period of time until you convince your victim that, about the double spending operation. So these are inherent disadvantages of the proof of work approach. And so people have, of course, tried to look at different alternative replacements for the proof of work concept. And remember, I told you that proof of work can be seen as a lottery or an election proportional to your work. So maybe let's try to base it on a different resource. Things that people have considered was basing it on disk space, so you would sacrifice some disk space instead of sacrificing some computation, or maybe trying to make the computation useful or make the storage useful. These were all attempts from one category where the resource is changed, but it's still a real-world resource. But what proof of stake is aiming to do is to actually consider a virtual resource or an abstract resource, namely the coin itself. And this is basically the idea of proof of stake. So let's move to the concept of proof of stake and to be able to contrast it with proof of work. So basically, it's a lottery or leader election process based on virtual resources. So the blockchain, the blockchain already contains, it maintains the ownership of a population of coins among all the participants. So the idea is, the original idea is simple. You just, if you want to add a new block, you elect an individual coin, and you look who owns this coin. This is written in the blockchain, so it's easy. And this party is actually entitled to create the next block. This was already proposed in the context of Bitcoin, and that's why this approach is called follow the Satoshi, because you just choose the smallest unit of the currency, which is called Satoshi in Bitcoin, and you look who owns it, and this is the lucky winner. And this means that the participants will be elected proportionally to the stake that they own. And it looks awesome because there is no need for burning electricity or hard disks, wasting hard disk space or any other real-world resource. However, the challenge here is, there are several challenges, but one that is easy to grasp is that for electing this coin, as I told you, you would need randomness. You need unbiased randomness that all the parties can agree on. Because we need to know who is the leader, who is eligible to create the next block. But if the adversary can bias the process in which this randomness is created, things get difficult, right? The adversary can try to bias the randomness in such a way that he will be elected to create the next block. And then he does it again and again. And this basically allows him to hijack the whole chain. So this makes it, difficult compared to the simple design of proof of work blockchain. So the first idea could be that, well, we have some randomness already in the blockchain. So let's just hash the blockchain and let this decide who will be the next leader. So we take the blockchain until now, we apply a hash function. This gives us something randomly looking, a particular coin. We look who is owning this coin, and this will be the party that will be allowed to create the next block. Sounds good, but not for long. If you think about it for a bit, here is a simple attack that the adversary can do, just to illustrate that this is not an easy problem. So imagine that the adversary owns some part of the coins, and just as it happens, sometimes he's elected to create the blocks, right? Because he does own some stake. So what he does is he does rejection sampling. So he tries to create a block, does the hashing, looks who would be the winner. But if it's not him, he will just discard it. And he will try a different block because he can just reorganize the transactions or do something with the block so that it hashes differently. He tries it again, and it again doesn't work out until he tries again, and it turns out he will be the winner again. And that's good news. So he publishes this block, and this makes him eligible to create the next block. And this is something he can do ad infinitum. So he basically hijacked the whole blockchain. So this is obviously a problem. And so we have to try harder if we want to design a proof-of-stake protocol. This is called, by the way, this is called a grinding attack. Yes? Is there interest in repeating this again? Okay, I can do that. So, sorry, I cannot hear you. So I can summarize this attack again, because this gives us some intuition of why it is difficult to establish a proof-of-stake system. So the proposal was that we simply, like the naive way how one could construct the proof-of-stake approach would be that we just hash the blockchain until now. This will give us a coin. Like this hash will tell us which, will identify one particular coin in the whole stake. And this coin, we will just look who owns this coin, and this will be the party that is allowed to create the next block. This is a process that everyone can do, and everyone will come to the same conclusion, right? So this could be a proposal, how to choose the next leader. But the problem with this construction is that if the adversary once gets the opportunity to be the leader and create the block, he can do the following thing. He might not publish the first block that he constructs. He can just remember that now there is no proof of work, so it's extremely cheap to construct blocks. You don't have to do any hashing, right? What you can do is just simply create a block. I mean, not you, but the adversary. He can just create the block, look who, I mean, not publish it, he just looks who would be the next leader. And if it's not him, he just discards it and doesn't tell anyone. But he's still eligible to create this block, right? Everyone agrees that he's the leader for this slot. So what he does is he tries again. He reorders the transactions. He changes something that the block format allows him to change so that the hash is different. He tries again. It's not him again. So he tries another again. Remember that this is extremely cheap, so he just does it on his local computer until he becomes the leader again. This will happen eventually. So, for example, if he owns 1% of the stake, he only needs to try on expectation 100 times. A very easy computation 100 times. So this happens within milliseconds. And once he finds a block that will hash so that he will actually be the leader for the next block, he publishes it. And according to the protocol, he is supposed to be the leader again. And he can do exactly the same trick again, which makes him the leader for all the following blocks. And this basically means he hijacked the whole blockchain, even though he only owns like 1% of the currency. So this is no longer a fair election of the leader, and this is a problem. So this suggests that we will have to be much more careful when trying to design the protocol. This is called a grinding attack, and this is like the simplest form of it, but there are many other variants of it, and these are things that we have to dodge when we are trying to design the protocol. But we are trying to do more than that. We are trying not to only avoid all the known attacks, we are trying to design a protocol that is provably secure against all the attacks under some assumptions, and this is what Ouroboros gives you. So Ouroboros is not the only proof-of-stake protocol with rigorous provable guarantees. I will survey a few of them here on this slide and also tell you how they deal with this randomness problem. So in Ouroboros, what is done is that the so-called coin tossing protocol is being run among the parties to generate randomness for the future. I will describe you in greater detail how this works. Another approach is taken by the Snow White protocol and Ouroboros Praos, which is the next version, which do use hashing broadly in a similar way as I showed you, but being much more careful and giving an analysis that this actually cannot jeopardize the security of the protocol. So not doing it in a naive way that I described, but doing it in a somehow different way. And a related protocol that should be mentioned here is Algorand, which is also a form of proof-of-stake protocol, but with a different approach. So it implements a complete consensus protocol for every block instead of applying the longest chain rule. And so it doesn't achieve what I described as eventual consensus, but it achieves full consensus for each of the block, which might incur some efficiency costs. But it still needs to get some randomness and needs to prove that the grinding is not a problem. And this approach also does it. But I will not talk about that because it's different to some extent. There are also some proof-of-stake solutions in the wild, so implemented ones, without provable guarantees, without analysis. There's the NXT cryptocurrency, which actually, if I'm not mistaken, at some point it used exactly the approach that I described at the beginning, but it evolved through a lot of steps, and the consensus algorithm has changed. There is Peercoin, there is DPoS that is used by several projects, which differs from our proposal. I will not go into the details. There is Casper, which has been discussed for several years now, I believe. But so far, the final form of Casper, I think, is not yet laid down, at least not in a way that could work without proof of work. Correct me if I'm wrong there, but I believe this is the current state. So let me talk a bit about Ouroboros, how it works. I will try to outline on a high level how we deal with these problems that I described. So from a very high level perspective, the protocol as it is assumes synchronous time and communication. So we have the time divided into slots, which are some periods, and we assume that messages get from one party to another within one slot. This is a strong assumption, and it is actually, we get rid of this assumption in Ouroboros Praos. But for now, and also for, let's say, didactic purposes, it's better to think about it in this model. So in each slot, the message gets from one party to another. You can just choose sufficiently large slots so that this is true. And it does provide the two properties that we care about, persistence and liveness, that I told you about, under two assumptions. The adversary has minority of stake under his control throughout the whole execution. So this is an analog to the assumption in Bitcoin that the adversary has minority of hashing power throughout the whole execution, right? Now we are making the lottery based on the stake, and so the assumption changes to minority of stake, right? So otherwise, you could do something like a 51% attack in Bitcoin. You could do it here if you owned 51% of the currency. And the adversary is subject to corruption delay. So the adversary can corrupt any of the players, and then the players completely give their state to the adversary. He can sign on their behalf. He can act on their behalf. He sees their messages and the keys and everything. But these parties together have to have minority of the stake, the corrupted parties. And if he decides to corrupt the party, it takes some time to corrupt the party. This is an assumption of the model. This one is also relieved in the Praos work, in the later protocol that I will tell you about. But for now, let's think about this. So in the communication model, we assume that the parties have synchronized watches. The time is divided into slots. And any message is delivered in the same slot, as I told you. All honest communication happens via broadcast, which is actually implemented by peer-to-peer gossiping, just like in Bitcoin. But the adversary is able to send arbitrary messages to arbitrary subset of the parties arriving at arbitrary times, and so on. So let's take a look at how it works. So Ouroboros splits the time, which I already told you consists of slots. These are the small intervals here. It splits it into epochs. An epoch is a sequence of R slots, and this is one of the colored rectangles in the picture. So there is a blue epoch, then there is a yellow epoch, and the red one, having colors for the purpose of this presentation. And now, for each of the epochs, so actually for each of the slots, so each of the boxes represents a block, and the block comes from a particular slot. So imagine each of these time intervals where the block is created to be, let's say, 20 seconds. That's the actual number in Cardano. So this is a 20-second interval, and for each of the 20-second interval, we want to elect someone who is called a slot leader, and this is the unique player that is allowed to create a block in that slot. Just as I told you, this is the spirit of the proof of stake, and we want to select him proportionally to his stake. And we want to do this for each of the slots. So how do we do it? Let's take a look how we elect slot leaders for this particular epoch, for the yellow one. So we need two things. If we want to sample slot leaders according to their stake, we need a stake distribution from which we will be sampling. So in which, for example, if you have 1% of stake, you will be sampled with probability 1%. If you have 10% of stake, you will be sampled with probability 10%. And we need randomness, as I told you, to sample from this distribution. So the stake distribution will be taken, the stake distribution to sample the slot leaders for the yellow epoch will be taken from a particular point in the blue epoch. So we just take a snapshot, we take a particular block, it's agreed upon which block this will be. We look who owns what in this particular block, and if you own in this block 10% of the stake, you will be elected with probability 10% for each of the slots in the yellow epoch independently. Okay, so this is the stake distribution. And the randomness comes from a coin tossing protocol that is being executed during the blue epoch by the parties. So in the previous epoch, right? And this is how the whole induction is happening. So then also during the yellow epoch, there is a coin tossing protocol running that creates the randomness for the red epoch and so on. So this is also why the protocol is called Ouroboros. This is a Greek mythological serpent that is biting its own tail. So you have this circularity that you need to create the randomness for the future epoch, but for creating the randomness, you already need the randomness from the previous epoch to be able to run the blockchain. And so we will call a leader schedule the sequence of the slot leaders for each epoch. So this would be the leader schedule for the yellow epoch. So let's take a look now at one particular epoch, how that operates. So if we look at a particular epoch, we assume that already we have a stake distribution that was taken from the previous epoch, and we have a randomness. Let's assume for now that it's ideal. Okay. So what we do is we select the leaders, as I told you, proportionally to their stake. This is just repeating what I sketched already. So there is a publicly agreed upon function L that basically takes this stake distribution from the previous epoch, takes the randomness that the parties have agreed on, and elects the whole stake leader schedule in such a way that independently for each of the slots, each leader, his probability of becoming a leader for that slot is proportional to his stake. And this schedule is public because everyone can compute, everyone knows L, everyone knows the stake distribution, everyone agrees on the randomness. So this can be computed by everyone. And so everyone knows who is the slot leader for a particular slot, and so only accepts block from that leader, right? The picture at the previous slide was a bit deceiving in that we don't require in every slot to have a block. So a valid blockchain can also look like this. There can be empty slots, of course, because parties might not act. They might be offline or something. As long as every block has an increasing slot number and every block is signed by the particular slot leader that is eligible slot leader for that slot according to the election that I described, then this is a valid blockchain. And then the parties simply accept the blockchain that is the longest one, just like in Bitcoin. So as I told you, the block looks, okay, just very quickly, the block looks like this. This is the usual stuff, what is in the yellow box, but instead of having a proof of work on top of the block, just like in Bitcoin, we include a signature by the slot leader that is elected according to the process to signify that he is actually the one that created the block. And if he is eligible, then this is a valid block. So let's take a look at the protocol now in one slide, and I'll try to highlight the similarities to Bitcoin. So again, the party, what it does in one particular epoch, it just collects all the transactions. It broadcasts, it collects all the broadcasted blockchains that it sees. It keeps only the valid ones and maintains the longest one as its state. And it basically just verifies whether it is a leader. This is a trivial computation. It's one, well, okay, if you know the randomness already and the stake distribution is just one sampling. So this is no work at all, almost. It's very simple. And if it turns out that you are a leader, you just create the block, which is simple. It's basically just one signature, trivial. And you broadcast this signature. And that's all. And everyone adopts the longest chain that it has seen. So it's a longest chain rule protocol almost just like Bitcoin. However, when we try to argue that it is secure, actually we are in a more difficult situation than in Bitcoin. So the argument in Bitcoin doesn't translate into this setting. And the reason is that our adversary is more powerful, right? Because it knows the entire sequence of leaders ahead of time, because as I told you, at least for the next epoch, you can compute the sequence of leaders at the beginning of the epoch, so you know who these leaders are. This is not the case in Bitcoin. You don't know what will be the sequence of people adding the blocks. And also the adversary can generate, if he is a slot leader for a particular slot, he can generate as many blocks basically for free, because every block is just one signature. This is not the case in Bitcoin. In Bitcoin, if you would want to create 2 blocks as a fork, you would have to create a proof of work for both of them. So this makes the adversary more powerful. And the question is, does this affect his power to derail the system and jeopardize the persistence and liveness properties that we want? The short answer is no, but the long answer is quite involved analysis in the paper, and I'm not going into that. But in the paper we prove that actually the adversary cannot do that, even though he has these advanced powers. So this was about one epoch, and now let's take a look at what happens with when we move to multiple epochs. I already sketched it in the first slide describing the protocol. So for the stake distribution to sample, so first, why do we need several epochs? It's because the stake distribution is evolving, right? Maybe at some point you own a lot of coins and later you send most of your coins to someone else. You shouldn't anymore be eligible to become a slot leader very often because you don't own many coins anymore. So we need to update the stake distribution according to how the stake is changing, right? And that's why we need epochs. We cannot fix a particular stake distribution. So the stake distribution is always taken from the previous epoch, as I told you. And where is the randomness taken? This comes from the coin tossing protocol that is being run during the previous epoch. And it uses the blockchain as a medium of communication. And the protocol has the property that it generates clean, perfect randomness, unbiased, that cannot be biased by the adversary, if a majority of the leaders in the epoch are honest. And this is a property that follows from the majority of stake being honest. What it uses is a publicly verifiable secret sharing, but I think I will not go into this because we are already over time a bit. So publicly verifiable secret sharing, I will just sketch it. It's a primitive that is known for decades in the cryptographic literature, and it allows us to construct this coin tossing protocol that has this property that if the adversary doesn't control majority of the stake leaders of the slot leaders for that particular epoch, he doesn't. The randomness is perfectly unbiased, and that's what we need for the next epoch election. And this allows us to prove 3 properties: common prefix, chain goal, and chain quality, which are properties that can also be proven for Bitcoin. I'm not going to describe the details of what these are, but it's known that these properties imply persistence and liveness. And so, after all, we arrive at proving that actually Ouroboros does achieve persistence and liveness under the assumptions that I told you. Here's one particular look at the security of Ouroboros, namely against double spending. This is a figure from the paper. This is how long you have to wait to achieve 99.9% assurance against adversary attempting one concrete attack, that double spending attack, which in Bitcoin you would just try to create a fork and invest your hashing power into hoping to create a longer chain. And in Ouroboros, you would do, in Ouroboros it's easy to describe, well, not easy, but it's feasible to describe how you would actually optimally approach such an attack. So you can see in minutes how many minutes you have to wait in Bitcoin. In Ouroboros, that's the right column, and the middle column called Ouroboros covered that gives even more favorable results to Ouroboros. But this is under the assumption that the adversary doesn't want to show himself and doesn't want to sign multiple blocks for a single slot. Because if you sign multiple blocks for a single slot, this is something you can do very cheaply, but everyone can then show these 2 blocks, and this identifies that you are a malicious actor, because someone following the protocol would never create 2 blocks for the same slot. So if you want to keep covered, it limits your attack opportunities even more, and then the waiting is even shorter. So IOHK has implemented Ouroboros in Cardano. This is implemented in Haskell. The whole code base is at GitHub, because the whole Cardano project is open source. The parameters in the implementation are 20 seconds for the slot, 5 days for the epoch, and currently it's already running in a bootstrapping phase where the staking is done by trusted servers, and public staking will be switched to public staking in 2018. Now I will just very, very quickly tell you about how Ouroboros Praos, the next version, differs from Ouroboros. Now that we have some high-level understanding of Ouroboros, I can just highlight the differences. And this will bring me to the conclusion. So Ouroboros Praos is the next version of Ouroboros, and it implements, it improves upon Ouroboros in two particular security points. The first one is that it works in a semi-synchronous communication model. Remember that in Ouroboros we assume that the communication is synchronous, meaning I send you a message, within the same slot you receive the message. Second, it also works despite fully adaptive corruptions. So this means if I'm the adversary, I can just point at someone whenever I want. After I learn that I want to corrupt this guy, I corrupt him, and immediately I'm in full control of his state, all his actions and everything. Remember, this was not the case in Ouroboros. So these are 2 strengthenings of the model that we take when we move to Ouroboros Praos. And we prove that Ouroboros Praos can operate securely even under these assumptions. And the tools that we use for this are local and private leader selection. So the leader selection is no longer public, as I described to you. Forward secure signatures, and blockchain hashing for dirty randomness. So the randomness is no longer obtained by the coin tossing protocol, but by some more sophisticated hashing, as I told you. And the randomness is not perfectly clean, but it's provably sufficient for our purposes. So let me dedicate 1 slide to each of these points. So
Peter, can you make a little faster?
Yes, yes, sure. This is 3 minutes. Unfortunately, we started late, so, but yes, I don't want to take more of your time. So the 2 strengthening that we make are, as I told you, the semi-synchronous communication. Basically, we change the model in a way that the messages can be delivered not in the same slot, but within delta slots, where delta is a parameter of the model, and the adversary has full control over this delay. So the red stuff is the difference in the model between the Ouroboros model and the Ouroboros Praos. So now the adversary has more power in delaying the messages sent by the honest parties. The second strengthening is that, as I told you, the corruption can happen immediately. And the tools that we use is that now we don't have this leader schedule that would be known by everyone, because this would not work in fully adaptive corruptions, because the adversary could just corrupt the leaders and he would be in control of the situation. So now every party can only find out for itself, for himself or herself, whether he is a leader, but no one else can find it out until the party produces a block, and this block is then broadcasted, and everyone can verify that this party was indeed the leader, but no one knows it in advance, so the adversary cannot corrupt this party. So this is the first tool we use. The second tool are key evolving signatures. For signing the blocks, we use signatures where each honest party, so the public key is still the same, but the secret key evolves. And so if the party follows the protocol and evolves its key, then if the attacker corrupts this party and gets the key, it doesn't know the past keys, and it cannot derive it from the present key, so it cannot create past blocks signed by this party anymore, even if the party is corrupted now. This is a very useful tool. And the last thing is that we use hashing for obtaining randomness instead of the coin tossing protocol, which brings huge efficiency improvements, but it requires careful analysis to make sure that this doesn't jeopardize the security. So that would be it. That was the overview of Ouroboros and Praos from a very high level. Thank you for your attention, and I'm happy to take questions if there is any time.
Evet. Soruları olan varsa alabiliriz.
Fazla zamanımız kalmadı zaten, bir sonraki session'dan da oturumdan da zaman yiyoruz şu anda. There is only, since we don't have any time, much time, there is only one question, actually some questions regarding grinding attacks, and how does this grinding attacks works, and then how does this rejection process going on? Can you make grinding attacks?
Grinding attacks?
Grinding, yeah.
Oh,
yeah.
the ones that I described.
Yeah.
So these attacks so the point of these attacks was where the adversary can affect the randomness, right, by the grinding. But if we don't derive the randomness by hashing, as we don't in Ouroboros, we do it by this protocol that comes from publicly verifiable secret sharing. Then this problem doesn't arise. I mean, it's a bit more involved than probably could be said in 30 seconds, but this publicly verifiable secret sharing and coin tossing protocol guarantees you that if the majority of stake is honest, then the randomness is completely clean.
Okay, yeah, thank you. Thank you for
Thank you.
Thank you, Mr. Peter Gaži.